Sorry, I actually missed class on Friday. I was here, but then at the last minute I was not feeling well and I had to go home. But I also wanted to show this to you. I should have actually brought, of course you can't really see anything. It just looks like a blob. But if you could see something, that would be a photo of me standing next to Jeff Emmel. Does anybody know who Jeff Emmel is? I'm so disappointed, okay? Jeff Emmel. He's the CEO and chairman of the board of General Electric, one of the largest corporations in the United States, you know, or in the world, okay? And they make all kinds of stuff, but one of the things that they make is medical scanners, medical diagnostic equipment, right? And so he's smiling there. And he was willing to take my picture with this picture with me because
it's blacked out.
It's blacked out. Okay. Because he cares about the stuff that I do, and the reason he cares about the stuff I do, you know what I do? I do this stuff, this weenie engineering mathematical equation stuff, right? So this is the real world. Okay. It's not just equations. If a guy like Jeff Emmel cares enough to get his picture, it means that there must be some external meaning to it all, okay? So when you're like thinking to yourself, why am I doing this? This is very painful. You know, this might be a little bit of motivation for you, okay? Venkat, I reviewed the lectures he did, and I thought he did a terrific job. We're a little bit behind in terms of number of lectures, but practically speaking, today I want to finish up the material of the stochastic sampling, and then that leaves us 3 lectures to do segmentation. And since the notes are not really on the website, are not fully updated, and they may not be, I'll have to see, and there has to be some logistical issues on campus, okay, that we might just go by notes that I do with the document projector. So I think next week 3 more lectures after this should be just fine, and that'll give you some time to get your labs done and to really review the material for the final exam. So I want you to go through it and really think about it all, and I'll get it in your head, okay? So I actually think it's nice if there's a study period between the last class and the final exam. And our final exam is on the Monday following the last class. So, you know, maybe you have a little breather in here. And I know we'll have classes, but to do some catching up. So use this time wisely, okay? Okay. All right. So with this, I'm going to go back to the document camera. Okay. Okay, so we're gonna. I'll do just maybe a quick review of what Venkat already covered, which is. Let me just do a quick review, because I actually, it's really disappointing for me, because I enjoy this material so much that I wish I got to cover it, but we did the Metropolis sampler, okay? So what you learned is that simulation methods stochastic simulation methods are methods for generating random variables from any distribution. Because, you know, like for instance, you generate Gaussian random variables, they're exponential. They're closed form expressions for how you can do that. But there are no closed form expressions for how you generate random variables from specific distributions. The reason that you can compute a random variable with a particular distribution is because, actually I think this is like problem 2 in chapter 2 or something, which is that you calculate the inverse cumulative distribution, cumulative density function, okay? So f is the cumulative density function, and then you compute sort of the inverse. This is the actual specific form, okay? And this always works independently from distribution. So even if it's like a singular distribution or really weird distribution, like the one I talked about at the beginning, like the Cantor function, it always works, okay? So no matter how weird the distribution is, this always works. And basically that was a problem you're supposed to prove that in chapter 2. And then you just put a uniformly distributed random variable into this function we call f inverse. And that random variable has the distribution. But you can't always compute this thing. First of all, you can't always compute the cumulative distribution. And if you can, inverting it might be hard, okay? So you can't always do it. So if you have a general distribution, how do you calculate it? So here's an example. You have an exponential, some crazy function. Well, this is a distribution. I don't know what this cumulative distribution function is because it's too complicated to integrate. But I'd like to be able to generate a random variable with the distribution. How do I do it? Well, that's kind of a good question. And that's what we're going to talk about. So the Metropolis algorithm was the first method that was proposed. It was actually, if you read this, they claim that Metropolis isn't the person who invented the Metropolis algorithm. I don't know what the details on that are, but in any case, it came out of chemistry, computational chemistry. They were trying to do modeling. So what they figured out was that you could have this crazy algorithm. Do you want to generate any probability, for example, from any probability distribution that has this form of equation 11.3, and all this, any probability distribution that's strictly positive can be put in the form of 11.3 because you just take the log of the density. But this is a Gibbs distribution, and what you found is that, okay, well, first you have a proposal distribution, but it has to be symmetric. That means the probability of guessing W, if you started at X, has to be same as the probability of guessing X if you start at W. It's a strong constraint. But if you start with this, then it turns out that there's a simple algorithm that will converge to the Gibbs distribution if you run it long enough. And then, first of all, what you do is you generate what do you do? Okay, you first generate a random variable with this is the proposal distribution. So you generate a random variable with the proposal distribution, right? So that's your proposal, okay? And over here there's a very important piece of advice. It says the theory of where's the very important piece of advice? It's over here somewhere. 13, 6, 45. 44, it says, here, I know I have an important piece of advice here somewhere. Okay, well, I won't worry about it. It'll come up later. Yes. It says right here, it says, in practice, there's severe restriction. This is a severe restriction because it's often the case that we might want to bias the proposals towards ones that are more likely to be accepted, right? And over here it has some useful advice. It says, this strategy is also highly recommended when pursuing funding, okay? So when you're pursuing funding, it's always best to bias your proposal towards something that you think might be accepted. Okay, so anyway, so you generate a random variable with the proposal distribution, and then what you do is you say, okay, basically you say, well, there's two possibilities. I can accept the proposal, or I can reject the proposal. I'm going to accept the proposal if its energy, U of X goes down. So I calculate delta E, which is the change in the energy. So, okay, and if the energy's gone down with the new proposal, I just accept it. If it's gone up, I accept it with probability E to the minus the change in energy. Okay? Now, if you think it through, that's exactly the same thing as equation 11.5. So the proposal acceptance probability is exactly this function, which is the minimum of 1 and this exponential. Because if the energy change is negative, then E to that number is greater than 1, and you can't have a probability greater than 1, so you just have 1, okay? So this is it. Now the part that's interesting is that you say, okay, well that's kind of reasonable. I'm going to accept it if the energy goes down. If it goes up, I'll accept it sometimes. Okay? But the interesting thing is that you okay, so that's this. The interesting thing is that you can prove that that's a ergodic Markov chain. Why? Well, it turns out that you can prove that this transition probability is a reversible Markov chain. So it follows the detailed bounce equation. And that's 11.6 is the transition probability. So this is why I spent all that time on Markov chains, because I wanted to be able to prove this result. And in particular, the detailed bounce equations. I remember I talked about birth-death processes and how they solve the detailed bounce equations. Do the detailed bounce equations always hold? No. The detailed bounce equations don't always hold. But when they do hold, then the full bounce equations must hold, and this thing must be an ergodic Markov chain that's actually reversible. Okay? So this is a reversible Markov chain. This is a reversible Markov chain, and the probability of any transition you can show is greater than 0. You can get from any state to any other state, because the proposal distribution has some probability of getting to any state, and then there's always some probability of being accepted. So you can always, in theory, get anywhere if you wait long enough with some probability. So therefore, it must be a irreducible. Okay, it follows the detailed bounce equations, which is equation 11.8. So that means it follows the full bounce equations, which is 11.9. So if it follows the full bounce equations, it's irreducible, okay, and we assume there's a finite number of states, and it's not periodic. It's easy enough to show it's not periodic. So it's not periodic, it's irreducible, and it's finite number of states. Therefore, it must be ergodic. That was the theorem that we had. So this has got to converge to a stable distribution, and the stable distribution it converges to is the Gibbs distribution that we started with. And the reason we know that is because in equation 11.8, the detailed balance equations have a stationary distribution of this Gibbs distribution. Okay? So that's the story. Okay. So what this all tells you is that if you wait long enough, this thing will eventually converge to a stationary distribution, which is the Gibbs distribution, and let's see. This is just more the same. Let me see here. Oh, then the Hastings Metropolis. Okay, so this is. Okay. The Hastings, now the problem with the Hastings is the problem with the Metropolis algorithm is that the proposal distribution has to be symmetric, and the symmetric proposal distribution, that might not be very convenient, and it might not be very efficient because, in theory, it's ergodic, this Markov chain, but in practice, if your proposals are crazy, they're going to get rejected almost all the time. So it's like, there's an old saying that if you have enough monkeys typing on a typewriter, you'll eventually get Shakespeare or something like that, okay? But the problem is you got to have a lot of monkeys typing on a lot of typewriters, of course, and it's hard to find any typewriters anymore because, nobody even has them anymore, okay? So it makes a lot more sense if you generate proposals which are matched to the distribution, maybe close, just intuitively. Proving this, by the way, is tricky. So I don't know that there's but what you want to do is generate proposals that are close to the true distribution, and then hopefully they won't get rejected a lot. Okay, and so here then what happens is, but the problem is is it still ergodic? Well, it isn't if you use the same transition rule. You have to use a different transition rule, and this is the transition rule you have to use. So your acceptance rates have to be biased in a way that compensates for the bias of your proposals, right? It's like, let's say you said you were going to generate random variables, okay? And you said, okay, well, is the random variable 2? And you go, no. And you go, okay, well, is the random variable 2? And you go, well, no. And you go, well, is the random variable 2? And you go, well, okay, fine, the random variable 2. Okay. Well, obviously, if I keep proposing 2 as the random variable, sooner or later it'll get selected. It's not going to be the correct distribution. So if my proposals are biased towards something that they just keep proposing over and over and over again, it's like, are we there yet? Are we there yet? Are we there yet? You know, eventually you'll just accept it. So there has to be something in the acceptance rate that corrects for the bias of the proposal. And that's what this term is here. That this ratio takes into account the fact that you're proposing something more often than you should. So it adjusts for that. And the expression of 11.10 then gives you the acceptance rate for the Hastings Metropolis. But so this is much more flexible and it's easier to implement, right? And this just is a simple example I worked up that shows, well, okay, if you use the Metropolis algorithm, and what'll happen is you keep proposing things that are crazy, and it just keeps rejecting it. And when it rejects it, the samples just remain the same. That's why if you look at the plot and figure 11.4 in the upper right-hand corner, that the samples just remain constant, okay? And then on the lower right-hand corner, well, this is when we do the Hastings Metropolis, because here what we're doing is we're generating samples that are close to the true distribution, so they get accepted more often. If our samples were exactly from the correct distribution, it turns out that you can show, relatively simply, that the acceptance rate in that case is exactly always 1. So, in other words, if the Q here is exactly the distribution that we desire, the P, you can show that all the terms cancel and the acceptance rate is 1. So if you pick a distribution which is exactly the correct one, then you converge very quickly in one case, sample, and your acceptance is always 1, okay? Now, your acceptance can be 1 even when you're not sampling from the true distribution. But if you are sampling from the true distribution, then it has to be 1. Right? So it's a sufficient but not necessary condition. Okay. Okay. So this is the example 5.2, 5.3. Now, okay. So that's all good and well and fine, but really, we're only talking about sampling from a scalar distribution of a single random variable. How do you apply this to a random field? Okay, well now what happens is that your proposal distribution is going to be typically not the replacement of all the pixels. A simple thing to do is just to replace one pixel at a time. So you have your proposal distribution is that the conditional distribution of the new okay, so what happens is this. Well, first of all, there's a conceptual issue here. That we have an array. So this is the Markov random field. It's a very small Markov random field, okay? So this is n equals 1, n equals 0. And then we get the next one. And this is n equals 1. This is n equals 2, right? Dot, dot, dot. Okay? So what happens is that as n increases in time, okay, you get a sequence of Markov random fields. Okay, so this is a little bit confusing. So each one is actually not necessarily a Markov random field, but it's a field. So you have a sequence of images. So you have a Markov chain of images. This is kind of a little, I mean, when you first hear this idea, I think it sounds a little weird, okay? So let me repeat it and make sure. So you have a Markov chain in time, right? So, okay, now, but the state of the Markov chain is something, right? Imagine that the state of the Markov chain is itself an image. So you have a whole image, and that's just one state of the Markov chain. So you have a sequence of images, okay? And you go from one to the next. And the sequence of images is a Markov chain. Wow. So that's a big idea because the state here is very high dimensional. It's a whole image. It could be a volume. It could be like 1 billion pixels, right? This is a very high dimensional state, but it can still be a Markov chain. So then the next image is formed by some statistical stochastic process applied to the previous image. So one obvious thing to do is say, well, what's our rule for transition between one time and the next? One obvious thing to do is to say, well, I'll just take one pixel in the image and just replace that one pixel. So, and maybe I'll replace it with some probabilistic rule. So I'll generate some random variable with some distribution. So the proposal distribution, well, I mean, I can think about the proposal distribution as being a distribution on the entire image, okay? But in practice, I only really need to specify the distribution of the proposal for one pixel. So I take this one pixel, and based upon its current value, I calculate a conditional distribution for the new updated pixel, and the only pixel that changes is that one pixel I've replaced. And now I go to the next pixel, and I replace it. So I go through sequence. I can raster through the whole image and replace each pixel with a new value, which is some probability based on some probability distribution, okay? Now, when I do that, and I replace one pixel at a time, is that going to be a homogeneous Markov chain? Any thoughts on the matter? So what does it mean for a Markov chain to be homogeneous?
Constant transition, well, constant time transition.
Yes, so the transition probabilities should not be a function of time, right? So are the transition probabilities a function of time if you're going through and first replacing this pixel and say that pixel and then the next pixel?
Seems like yes.
Yes, right? Because in the first case, I'm only replacing this one pixel. And in the second case, I'm replacing a different pixel. So clearly, I can tell there's some dependency on time, right? So it's no longer the case that this is a homogeneous Markov chain. And if it's no longer a homogeneous Markov chain, then the rules of our methods don't apply, right? So how are we going to fix this, okay? Okay, so the way we fix it is, well, intuitively, it seems like, okay, we're violating the letter of the law, but it doesn't really feel like we're violating the spirit of the law, right? I mean, okay, fine. So we're going from one pixel to the next, but it's not really changing, okay? Okay, here's a Gedanken experiment. You can say, well, what if I randomly select a pixel with a uniform distribution over a set of all the pixels, okay? And then I replace that pixel. Well, then that would be a homogeneous Markov chain because I've selected the pixel randomly, and then that's the pixel I've replaced, so the transition rule at each time is the same. Now, if I do n changes of transitions, it doesn't mean every pixel got changed, but if I wait long enough, with probability 1, every pixel will get changed eventually. So the random update thing works fine, but in practice, you don't do random update. You usually do a fixed order update. So how do you jive that all together? Well, okay, first of all, this happens. You first say, okay, you're going to use a Hastings Metropolis algorithm for the update. That's equation 11:15 and 11:16. So that's the probability of acceptance you're going to have for your proposal at each pixel. And now everything gets indexed. The proposals get indexed by the pixel location. So the equations become a little different because everything has to be indexed by S sub I, where S sub I is pixel to be replaced, okay? And now you know that by the same logic as we had before, that the full balanced equation will hold, it's just that it's going to be non-homogeneous. So there's a transition probability, and if the incoming distribution of the image, so this is the equation at the bottom of page 255, and the incoming equation distribution image had the desired Gibbs distribution, then the new image would have the desired Gibbs distribution, because the proof we gave for the Metropolis-Hastings before, that part goes through. So that holds. The problem is it's not a homogeneous transition, so since it's not homogeneous, it's not necessarily ergodic. So how do we fix it up? And the fundamental problem is just that this P here, it depends on S. Well, you can fix it up by, on page 256 at the bottom of the page. That's sort of the solution. The solution is, well, you just multiply all the transitions it takes. So in other words, in one iteration, you replace each pixel once. So if you do that, and if you use the same fixed ordering from iteration to iteration, then the probability distribution, the probability distribution, so in other words, okay, what happens is this. In this picture here, you have a whole image and you replace one pixel, you have another whole image, so you have a whole sequence of transitions, right? So let's say there's only 4 pixels in the image. So then after 4 transitions, you've replaced every pixel. Okay? So you've replaced every pixel after 4 transitions. And then if you consider this, if you just take this state here as the beginning, right? And then if you replace every pixel, then you take that as the next state, right? And then if you replace every pixel again, that's your next state, right? Well, that's a subsampling of the Markov chain. Now, if you recall, in one of the earlier sections, because I've been very clever to only insert what's necessary into these notes, because I know all these topics, you can take any one of these topics and teach a whole course on it, okay? But I just want to give you the basics so you can actually do useful things, so someday you can meet Jeff Enmel, okay? Or whoever his equivalent is. So, what happens when you subsample the Markov chain, you get what? What happens when you subsample a Markov chain? You get another Markov chain. So the subsampled Markov chain is a Markov chain. What do you know about the subsampled Markov chain? The original Markov chain, it has if you start with a Gibbs distribution, you get a Gibbs distribution in the next point. Okay, so the Gibbs distribution is the stationary point of the transition probability, but it's not a homogeneous Markov chain. But if you now subsample it,
It could be homogeneous.
it's homogeneous, right?
Right.
Because now you've replaced every single pixel in the same order every time, okay? And guess what? If you start off with the Gibbs distribution at this point, and you take these transitions, what are you going to come out with? Because if you start with the Gibbs distribution here, and then you did a replacement of a single pixel, you'd still get the Gibbs distribution. And if you did it again, you still get the Gibbs distribution. The Gibbs distribution is the sort of the stationary point of these transitions, okay, by construction. So if you do n transitions, and you start off with the Gibbs distribution, you'll have what?
Still Gibbs.
You'll still have the Gibbs distribution. So the Gibbs distribution is the stationary distribution of this subsampled Markov chain, right? It's the fixed-point distribution in the sub. So it obeys the full balance equation. It obeys the full balance equation for the homogeneous subsampled Markov chain. Now we're good, because we got a homogeneous Markov chain, which for which we know that the full balanced equations are solved with the Gibbs distribution that was the desired distribution. So, now what do we have? We have an irreducible Markov chain, which is homogeneous, aperiodic, it's easy to show it's aperiodic, and has a finite number of states, so it must be ergodic and converge to the solution to the distribution, which is the solution of the full balanced equations. We know that this method will produce a stochastic sample with the Gibbs distribution as their asymptotic solution. So this is a way of generating samples from the Gibbs distribution. So the only thing here, and you know, usually actually if you look at material in this, people sort of brush over this point, but I just felt it was intellectually dishonest to brush over the point, is that people prove the results of the reversible Markov chain, but they're really not applicable directly to the multi-dimensional case where you're sampling a Markov random field that's a vector, pixel-wise. So this is the proof that, yeah, it's correct. It'll still converge to the correct distribution. Because there's a subsampled Markov chain, which is a homogeneous Markov chain, and it must be ergodic. Okay? Is this making sense? So the bottom line is this. You can, and that's what this theorem is here, theorem 5. That basically it says that you can go through and you can replace pixels in sequence. So this is the bottom. This is the idea. This is what you actually do in practice, and you're going to actually implement this in lab 3, right? So when you implement it in lab 3, I think it'll become clear. So you have, this is your random field. Now you have some distribution, right? You have some distribution, and what you do is you replace this pixel with a, okay, well actually I'm going to, okay, so you replace this pixel, you generate a proposal for that pixel, and you accept or reject it with a probability related to increase in energy, right? And then you go to the next pixel and you do the same thing, and you just go through, you raster through, and you replace pixels with using this algorithm, okay? And if you keep doing this over and over and over again, eventually what happens is that the distribution of this Markov random of this field converges to the distribution of the Gibbs distribution, and remember, Gibbs distributions are just the distributions of Markov random fields, right? Because that's what we learned in the previous chapter. I think it was chapter 10. So this is a way of generating a sample from any Markov random field. See, we never actually discussed how to generate samples from Markov random fields. We talked about the distributions, but we never described a way of actually generating samples from those distributions. This is how you actually achieve that goal. Now, there's a technique called the Gibbs sampler. So the Gibbs sampler is so incredibly intuitive that, like, once you understand it, it's hard to remember why you wouldn't have always known it was true. Okay? Okay? So what happens is this. You have a Markov random field. So, okay, so let's say this thing is an MRF. You have a Markov random field, and let's say, hypothetically, it's got a neighborhood, it's got an 8-point neighborhood system, right? So what's going to happen is you take one pixel here, and you say, what's the conditional distribution of that pixel given all the other pixels in the image? Well, in practice, it's only going to depend upon its 8 neighbors, right? Now, if it's more than 8 neighbors, fine. Whatever it is, it's the number of neighbors in the Markov random field, right? It can even be spatially dependent neighborhood, it doesn't matter. But in any case, that pixel will have some distribution given its neighbors. So calculate the conditional distribution of that pixel. We'll call it PS of XS given XR for R not equal to S, right? So this is the conditional distribution of a pixel given its neighbors, okay? And I just calculate that conditional distribution. Now, this is only a 1D distribution. So it's pretty easy usually. If this is a discrete random variable, x may only take on, I don't know, let's just make something up, 10 values, okay? Because it's a random field which is discrete. So maybe, or it could be 256 values, okay? I don't know. It doesn't really much matter. It's a finite number of values. Even if it's not finite, you know, maybe you can calculate the distribution here. You can just numerically integrate it so you could get the cumulative distribution function, and you can exactly calculate the inverse cumulative distribution function of equation 11.1. So now you can generate a random variable with the exact distribution of the conditional distribution of a pixel given its neighbor. And the important thing is that only depends on its neighbors. So I don't have to do this operation, I don't have to know all the pixels in the whole image. I only need to know the neighboring pixels. Okay? So I generate a random variable with the correct distribution given its neighbors. Then I get to the next point, and I generate a random variable with its correct distribution given its neighbors. And I go through and I just keep replacing pixels with the distribution they should have given their neighbors. And I keep doing that. Now, if there's any justice in the world, if I do that long enough, eventually it should converge to the correct distribution, right? If I tell you, okay, this is supposed to be the distribution of the whole Markov random field, and I start this thing off at zeros, and I replace one pixel with this conditional, a sample from its conditional distribution, and I do the next one with the next, and I keep just enforcing this constraint that the pixel has to have a certain distribution given its neighbors, right? And I just keep doing this and doing this and doing this and doing this, okay? Is there any justice in the world? No. There's no justice in the world. But if there is any justice in the world, then it should converge to the correct distribution, right? Doesn't it seem reasonable? Does anybody, you see what I'm saying here, by the way, right? It's just, I'm reinforcing a consistency condition, right? It's like if I'm solving a differential equation, like Laplace's equation, and I replace each pixel with the value it should have if Laplace's equation is solved, and iterate through, you would hope it will eventually converge to the solution of the Laplace's equation. In fact, that's the Jacobi method, okay? Yeah.
What's going to happen if you run the algorithm in parallel on all the pixels at the same time?
It's an interesting question. Now, if you replace two of the pixels that are right next to each other at the same time, that's a problem. But as long as they're separated so that they're not neighbors to each other, you're actually okay. You can replace this pixel and that pixel simultaneously.
And would it converge a little faster?
Well, it will converge like much faster. It depends upon how you interpret it. If by convergence, if you ignore, if you consider one upstate with like n processors, if you count the number of clock cycles, it's like a lot faster because now you have a lot more processors. But if you count the clock cycles times the number of processors, then it'll be the same. But if you have a parallel machine, which happens a lot these days, then yeah, you definitely want to take advantage of that. This is what's called embarrassingly parallel, okay? So it just runs completely decoupled. As long as there's a thing called a coding, and as a matter of fact, I talk about that in some of the notes, so I don't think I've gone over in too much detail on this thing called the pseudo-likelihood estimation method. I think that was in the last chapter. Maybe NCAT went over it. And there's a thing called a coding, so you could break it up into groupings that are decoupled. And
so basically, the total number of pixels divided by 8.
In this case, yes. Correct. Exactly. Right. So, okay, so if there's any justice in the world, you would expect this to converge, right? Because you're reinforcing that you keep replacing pixels with their correct distribution. It's like getting a bunch of kindergartners to behave or something. You say, okay, sit in your seat, sit in your seat, sit in your seat. Okay. So each pixel, if it's misbehaving, you replace it with the distribution it's supposed to have, okay? And you just keep going around in hopes that it should eventually be all self-consistent. Well, guess what? I can prove that that's correct. And this is how. So, this is section 11.5, okay? So what happens is that we have this is the Gibbs distribution, okay? P of x, okay? And, okay, now, and this is, we're assuming this is like a Markov random field, right? So it has some neighborhood. Now, if I calculate the conditional distribution of a pixel given its neighbors, it has this form of the equation on the bottom of page 258. And it's, the important thing is it only depends upon its neighbors. You guys have done this calculation, right? So, this is 9. So what happens is this. If you use as your proposal distribution, the conditional distribution, so this is the second equation on page 259. If you use as your proposal distribution, the conditional distribution of a pixel given its neighbors, okay, then if you plug in for the Hastings Metropolis sampler, it turns out that in that case, the acceptance probability is always 1. Because everything just cancels out. That's equation 11.17. Go through that and check it. So in the special case where you replace each pixel with a sample from its conditional distribution, given all the other pixels, you always accept the result. So then you don't even have to do the rejection thing. So you just skip that step. So it turns out that this technique of replacing every pixel with a sample from its conditional distribution is exactly the Hastings Metropolis sampler, okay, with just a different proposal distribution. So it inherits the properties of the Hastings Metropolis sampler. It's ergodic because it's a homogeneous. It's a subsample version is a homogeneous Markov chain, which is reversible and obeys the full balance equation and is aperiodic and has finite state, so it has to convert it to ergodic distribution. So, in fact, in this particular case, there is in fact justice in the world, and it does converge. And if you look at this result on page 260, this is a result of what you're supposed to do in the lab, more or less, I think. And what it shows is that if you run enough iterations, well, you start off with like a random, uniform random distribution. So every pixel is independent, and you pick it to have a 50-50 chance of either being 0 or 1. Okay, that's the initial condition. And now you start just replacing pixels with samples with samples from the conditional distribution of that pixel given all its neighbors. And you run it, and if you run it for like 100 iterations, okay, and here we pick beta equal to some value. I think beta is 1. Okay. Now if you remember, beta 1 is above the critical temperature because the critical temperature is something like 0.8. So this is above the critical temperature. If you run it for enough iterations, guess what? It turns to almost all white or almost all black. Of course, I kind of cheated here and ran it a bunch of times and then selected 2 kinds that came up white and 2 that came up black or something like that. Okay, but if you run it enough times, it always turns to either white or black. Now, why is that? You say, well, that doesn't seem like a stationary distribution. Well, because what happens is that this shows that the true distribution of this Markov random field is really clustered around, essentially, the distribution has 2 clusters to it. This is sort of like a conceptual idea, okay? But if you have, the one cluster is peaked around 0, and the other cluster is peaked around 1. All zeros, and the other one is all 1, okay? And what happens is that, now if you run this, it's an ergodic Markov chain. So if you run it long enough, eventually, if it gets into the state of all zeros, it'll eventually find its way into the state of all ones, and then it'll find its way back. Because it's irreducible Markov chain. So it'll eventually get there. Except, it could be extraordinarily long amount of time. It could be like billions of years, okay? It could be a Googleplex of years. Okay? I don't think it would be quite as bad as Googleplex, but it could be really long. And if the image is really big, the amount of time it could take could be a lot longer, okay? Because the problem is this. In order to make this transition from 1 to 0 or 0 to 1, you've got to go through, and what will happen is that when you go to replace a pixel, so let's say all the pixels are zeros, or most of the pixels are zero, then if you're like 1, you're like different than your neighbors. You're like, oh my gosh, I'm different than my neighbors, okay? So, well, once in a while you'll produce a 1, but the probability, so what would have to happen is that you'd have to have, like, produce a whole bunch of 1s by some extremely rare event, and then you'll produce so many 1s that the whole thing would flip to 1, and then you go there. But that's like the probability that all the monkeys are going to hit the typewriter and Shakespeare is going to come out. Right? I mean, it can happen, but it's extraordinarily improbable. So in practice, these Markov chains theoretically are ergodic and do converge, but in practice, they're almost reducible. It's not really true that they're technically irreducible, yes, but mathematically irreducible. But practically, they're not really irreducible. In fact, they have a set of states that are almost separated. The chance of getting from 0 to 1 is extraordinarily small. So it's almost like there are two Markov chains. There's two, the states can be separated into two sets that are almost disconnected. Because the probability from getting from one to the other is extraordinarily small. So you have to be very careful when you're using these techniques, because sometimes you can fool yourself. Yes, theoretically, if you run this for an infinite amount of time, eventually it will become an ergodic Markov chain, but that could be really a long time, okay? So you have to be careful when you're using these techniques that you're getting meaningful information out when you do the sampling, okay? But I think it's a really nice application. And from the previous time, we talked about this. We talked about how the convergence of these Markov chains is always exponential because the eigenvalues converge geometrically. But some of these eigenvalues can be so extraordinarily close to 1 that, in fact, the convergence could be really, 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 really slow. Where really slow means like it could take the amount of time it's going to take for the rest of the unit is the length of the universe. Like so slow that it's ridiculous, it's absurd, okay? Any questions about that? You're going to do this in the lab, okay? So, in the next class, we only have a couple more minutes, but in the next class, I'm going to talk about discrete, about actually now using these discrete Markov random fields as priors in applications like in Bayesian segmentation, okay? And the idea here then is that you have some kind of observation, and then what you're trying to do is estimate a discrete random field that represents the class of each pixel. So that's a typical application where a discrete Markov random field can be useful. And so this is a little bit like, this is very much like the generalization of the hidden Markov model to 2 dimensions. So the hidden Markov models were really beautiful because we could do all kinds of closed form analysis, and they're very useful in lots of applications, like in speech modeling. But in 2D, the concept of a hidden Markov model basically breaks, because the hidden Markov models, what you needed to do to train them and to estimate the states is you had to run the forward-backward algorithm, and you had to run the dynamic programming algorithm. The dynamic programming and the forward-backward algorithm were very similar. They're very small variations, but they're both based on this idea of having a future, a past, and a present. There's no future, past, and present here, okay? So it doesn't work, and that's going to be a fundamental challenge, and it's perhaps the fundamental challenge of this field. Okay, so let me see. Okay, so here I am. It's nice seeing you. Enjoy your turkey. Don't eat too much, and I'll see you after the break is over. Goodbye, and have a very nice holiday. It's been nice seeing you today. We have 2 more seconds. Bye.
Recording has stopped.
So when, if you have